Thank you. Hello, everyone. Welcome to the JINA online seminar. Today we have Jack Bishop from University of Birmingham, who has experience in nuclear applied physics and fundamental physics. And today he talked about clustering in boron-9 as a test of mirror symmetry. It's your time, Jack.
Brilliant. Thank you very much. So thanks for the kind invitation to talk to everyone this evening, or I guess this afternoon, where the majority of you are. So yes, I'm going to be talking about clustering and boron-9 as a test of mirror symmetry. There's a few different things there. So what I'm going to do is I'm going to go through each of these in order. So I'm going to start off by giving a gentle introduction to nuclear clustering, for those of you who aren't familiar with this idea, before talking a little bit about mirror symmetry and where it's useful, before going on to talk about the interesting example here, which is looking at the mirror pair of beryllium-9 and boron-9, and then talking about a bit of an experiment, some theoretical calculations, and sort of more broadly about what's going on in terms of these mirror systems. So let's kick things off by talking about nuclear clustering. So we start off with a very simple question. So we look inside of our nucleus, and what we want to ask ourselves is, what does a nucleus particularly look like? So what you get taught in high school is that the nucleus is just sort of this very boring sphere. You've got protons, you've got neutrons, and in the liquid drop model, you just sort of add those onto the nucleus, and you end up with this sort of liquid type configuration that ends up a bit like a sphere. And what we see is that this spherical description works as a first order approximation okay in some areas of the nuclear chart, but actually the majority of nuclei are not spherical at all. So what we see is that some nuclei have this sort of quadrupole deformation, so they can kind of be a bit like the Earth and all of us this time of year, we're a little bit fatter around the middle, or they can sort of be squashed down into a rugby ball shape. And actually some nuclei are even more interesting than that. So you can have octopole deformation, where it's sort of starting to look a little bit more like a snowman. But really the take-home message here is, we don't have to stick with this sort of boring sphere. So actually, energetically, there are other configurations that may be allowed that will actually exist inside of the nucleus. So rather than thinking about the protons and neutrons as our building blocks for our nucleus, what we can start to do is we can think about having something as a substructure, which is the alpha particle. So here what we do is we're combining together two protons and two neutrons to form these alpha particles. And what we see is that this is a very stable configuration. So they have about 7 MeV per nucleon binding energy, so they're very stable. And what we can do is we can think about how, in particularly light systems, what we see is that the n equals z are usually the most stable configurations. So this kicked the idea off back in the day that we can start to think about these nuclei being formed of these sort of geometric arrangements of alpha particles. So this doesn't necessarily have to take place in the ground state. So we can think about a system like carbon-12. So in carbon-12, we've got 6 protons and 6 neutrons. So in the ground state, everything's sort of closer towards this spherical arrangement. But what we can do is we can give energy into this system. And what happens then is we have a system where we have the nucleus in carbon-12 starting to look a little bit more like a triangular arrangement, something like that, of these 3 alpha particles in the 6-sided state. And this is sort of the stereotypical, the archetypal cluster structure that you hear people talk about a lot. So this 3 alpha particle arrangement in carbon-12. And it's so often talked about that it's actually got a very specific name. So this is a resonance that is known as the Hoyle state. So there's a lot of very strong evidence for clustering, and particularly if we focus in on the Hoyle state in carbon-12. So we'll kick off by talking about where it actually gets its name from. So when we're looking at the helium burning phase of stars, what we're doing together is we're bringing together helium nuclei, and we bring together these 2 helium nuclei, and we get together to beryllium-8. And beryllium-8 is unstable, it has a lifetime about 10 to the minus 16 seconds. So constantly these helium nuclei are fusing together and they're just decaying straight apart again. So because this is happening in stars, we have this sort of dynamic equilibrium taking place where we have one of these beryllium-8 nuclei to about 1 billion of these helium nuclei. So because we've got this equilibrium, what can happen is before that beryllium-8 has a chance to decay, a third helium nucleus can come in and it can actually interact, and then this brings us up towards carbon-12. And because the Q value for adding together this alpha to this beryllium-8 is so large, we end up with our carbon-12 nucleus in this highly excited state. Okay. And what these stars need to do is they need to go and make carbon-12 in its stable configuration. So it needs to get down towards the ground state. But actually, through 2 gamma decays, this only happens a very, very small fraction of the time. And actually, 99.9% of the time, it breaks back apart into 3 alpha particles. So when people were looking back at this process, so this is called the triple alpha process, and they were trying to see in our universe, okay, we can see how much carbon, oxygen, neon, magnesium, everything above here that we have in our universe. And what they saw was that this process just didn't really account for the amount of that heavier stuff that we see in our universe. So what Fred Hoyle, who's a British astrophysicist, said is that there must be a resonance with exactly the right properties in carbon-12 that actually enhances the production of this by several orders of magnitude. So if we look and think about how we're actually producing this, so we're bringing together this beryllium-8 with an alpha particle. So the configuration to make this reaction happen in a much faster way must already have some sort of strong alpha clustering component for this actually to be able to take place. So what we can do is we can think about some of our nicest models. So there's a particular theoretical model, AMD, which is anti-symmetrized molecular dynamics. And what this allows us to do is basically let the protons and neutrons do whatever they want to do. They're almost free. And what we're looking at is certain stable configurations inside of the nucleus. And what we have here are some calculations from Canada Enyo. And in the center, we see this is the configuration that is actually predicted by theory for this Hoyle state, where you see you've got this beryllium-8 on the right-hand side, you've got an alpha particle here, and it behaves a little bit like this triangular configuration we talked about before. And what we can actually do is we can bring those 2 things together nicely. So if we take a group theory approach, so we can look to these algebraic cluster models, we'll actually combine the 2 together very nicely. So what you can do is you can think about you've got a quantum mechanical object that is a triangular arrangement of these alpha particles. We can add energy into the system. We can start spinning it by its different about its different axes. And what you get on the right-hand side is a prediction of a series of states if we have this triangular arrangement. And what we see on the left-hand side are the experimental states that have been measured so far. And actually, it was this measurement of this 5-Haas state in the ground state rotational band back in 2014 by Damir and Lambari that actually showed that Beaker and Ikeda's model of this triangular arrangement really worked together to show that actually the carbon-12 nucleus can be described fairly well by this triangular arrangement of alpha particles. So, of course, that's not the only example of clustering. I'm showing you one very specific example. One example isn't really enough to talk about generally about clustering. So what we can ask ourselves is about whether we can extend this idea to other systems that can be made solely of alpha particles, these so-called alpha conjugate systems. So this is encoded in this idea called the Ikeda diagram. And what we do is we go and we just keep on adding alpha particles into our system and thinking about the expected energy that we expect these various systems to occur. So what Ikeda said was that we expect this particular type of clustering to happen just at or above the separation energy of these particular systems. So actually the ground state of beryllium-8, it's unstable, but it's actually a very well-developed 2 alpha cluster structure. So it's sort of like a dumbbell configurations. You just got 2 alpha particles basically stuck together, and that's a very nice system. The carbon-12 example we saw before at 7.6 MeV is then sitting just above carbon-12. Then we can go to oxygen, neon, magnesium, silicon, and so on and so on. So this is an area that has been developed for a large period of time. But actually what we can start to do is start to ask a slightly different question. So this is moving away from systems solely made up of these alpha particles. And what we can do is we can move to this sort of extended Ikeda diagram. So what we can do instead is we can think about something like our beryllium-8 nucleus, which looks a little bit like this. And what we can do is we can add into that a proton or a neutron. And what we want to ask ourselves is whether this clustering, this alpha clustering, is still going to survive when we add these protons and neutrons. So we can think about adding a proton and neutron to beryllium-8. We get this boron and beryllium. I mean, the sort of spoilers in the title that that's going to be the focus of today's talk. We can also think about adding a proton or neutron to carbon-12 to look at nitrogen-13 and carbon-13. You can even do this by adding 2 protons and 2 neutrons at the same time to look at a mirror pair like neon-18 and oxygen-18. So what we want to ask ourselves is the second question of, okay, if the clustering does survive when we add a neutron into the system, does it actually matter whether we add a proton or a neutron? Because what we'll see is that they're actually very similar, apart from the fact of the Coulomb interaction. So this brings us on to our second idea here, which is this idea of mirror symmetry. So fundamentally, the idea behind mirror symmetry is that the nuclear force doesn't care about whether you're a proton or a neutron. So this is the charge independence of the nuclear force. And this essentially arises because the mass of the neutron and the mass of the proton are effectively approximately the same on the energy scales that we're looking at. Of course, as I said, the only difference there is going to be that the proton is going to have an additional electromagnetic interaction. So we get very slight differences due to the Coulomb differences. But otherwise, when we swap our neutrons and our protons, the states and our nuclear physics behavior, we expect to be the same. So what we can do is we can look at this in action. So what we have here are the level diagrams for oxygen-17 and fluorine-17. So we've got a nice doubly magic nucleus. We're adding either a neutron or a proton onto the system, and we're looking at the resonances that we can predict from this system. And what we see is that the ground states are both 5½ plus. The first excited state is a 1½ plus. Then we have a 1½ minus, 5½ minus, and the energies in these two systems are effectively going to be the same. So this is a very powerful tool when you're studying a system that has a mirror where you change all of your protons into neutrons and neutrons into protons. And actually, this mirror symmetry is very, very useful for studying a completely new system when it's effectively next to something that has been very well understood. So what we know is that the spin parities and the properties of these states are going to be the same with this mirror symmetry. So that brings us on to our beryllium and boron mirror system. So if we look at the same diagram for beryllium and boron, what we see is that, again, the ground states both have the same spin parity. They're 3½ minus. We see that there's some excited state, and then 5½ minus, 1½ minus, 5½ plus. But actually, if we look at the first excited state, this is relatively well seen in beryllium-9, but actually beryllium-9 and boron-9 end up being quite different. So beryllium-9 is stable. So the first way that it can actually decay is if we go above 1.66 MeV, we get to the neutron separation energy, and it can actually then spit out a neutron, and we end up with our beryllium nucleus. But actually, in the ground state, boron-9 is unstable. So it's unbound by 185 keV to proton decay, so it lasts only 10 to the minus 16, 10 to the minus 17 seconds. So that's not really a problem for our mirror symmetry. It just means that one of them is going to be a little bit harder to study. So the ground states, as I said, those are both 3½ minus. The first excited state, if we look in beryllium-9, is a 1½ plus state. But actually, if we look in boron-9, there's kind of this approximate idea here saying around 1.6 MeV. So beryllium-9, the 1½ plus state, can actually be studied fairly well. You can cause, for instance, electromagnetic excitation from the ground state to this excited state. And actually, it's quite interesting because this is what we call a virtual state. So this is a neutron in a S-wave orbital. So there's no centrifugal barrier. There's no Coulomb barrier. So we end up with this very odd shape that is called a virtual state. But actually, in the boron-9 system, it's a lot harder to actually be able to study this 1½ plus state. So we cannot excite boron-9 either as a beam or a target. So we have to start very carefully about choosing a method that actually allows us to populate this 1½ plus state to work out what excitation energy it is and trying to understand about how good this mirror symmetry is in the A=9 system. So that brings us on to our experimental searches. So what we can do is we can look at the previous experiments that have been done. And we start at the top. You see that there's actually a collection of states that seem to be in fairly good agreement, all using this helium-3 T reaction. they get an energy of around 1.8 MeV, but then we start to get some different outliers. So there's kind of a selection here where they're only seeing a state around 0.8 MeV. There's one that's kind of in the middle here saying 1.3, and then there's a few more that sort of agree with this higher energy system. So there's obviously something slightly odd going on here. And what we're really seeing is the fact that there's actually almost two regions or claims that you could have two potentially different states, two different 1.5+ states. But the key point here is that actually we don't see two 1.5+ states in our beryllium-9 system, so we shouldn't expect to see two 1.5+ states in our boron-9 system. So back in 2021, when I was working at Texas A&M, this is kind of when I started to get into the Boron-9 game, and we were asking ourselves again a kind of slightly different question. So what we were interested in is not looking at two alphas plus a proton, but actually three alphas plus a neutron. So this is looking at this nitrogen-13 system, and what we wanted to see is whether we saw two distinct types of clustering. So the first that we expected to see is where we've got this triangular arrangement, as we saw in carbon-12 for the Hoyle state, this triangular arrangement, and we've got a proton that's maybe, if you think about it semi-classically, kind of doing some sort of orbital around this system. The other option we can have is actually what we have is a boron-9 system, so something where we've got two alpha particles and a proton, and then it's the alpha particle itself that's kind of whirring around the outside. So what we were asking ourselves is whether we see either of these two particular types of structure, and then again, do we see those same structures as we see in carbon-13? So as I said before, boron-9 is rather difficult to populate. It's also the same issue getting to populate these high-lying states in nitrogen-13. So I won't spend too much time delving into the details of this experiment. But what we did here is we populated these high-lying states in nitrogen-13. We need to get to high excitation energy because we need enough energy to be able to break apart that nitrogen-13 into these 3 alpha plus proton final states. So what we did is we sent a radioactive beam from the Mars beamline down of oxygen-13 into our time projection chamber. We stop this oxygen-13 inside of our detector, and what we're able to do in this time projection chamber is we're able to see the tracks of all of these decay products. By looking at how far they travel in our gas, we can work out their energies and their momenta, and this allows us to try and see exactly what's taking place with these different types of clustering. So this is an example of a real event. So this is a 2D projection of the 3D image we see. So the decay is taking place around about where the cursor is, where the yellow part is. These heavier tracks here correspond to the alpha particles, and this light blue one here that's going off towards the bottom left is our proton. So what was quite nice, so this wasn't really the aim, but this was actually the first time that this new decay mode has been seen. So this is beta delayed 3 alpha plus proton decay mode. So this is fairly rare that you can beta decay and then a particle is splitting apart into 4 constituents. Okay, so we didn't really care too much about the fact that we were getting this beta delayed 3 alpha plus proton. What we could do is we could look at the pairs of 2 alpha particles plus a proton and look to see how this nitrogen-13 system was decaying. And what we expected was actually that nitrogen-13, it would spit out an alpha particle and it would go to the boron-9 ground state, which would then decay. But what we saw is actually for something very slightly different. So what we have on the screen is the relative energy between 2 alpha particles and a proton. So this first peak we see here that has this sort of dashed red line is the contribution we expected to see from the ground state. But what we see is that there are also additional high energy contributions that we saw. Now, of course, the statistics here are very poor, but actually what we see here is possible proof that we're seeing a contribution where we're seeing states decaying not just through the boron-9 ground state, but also decaying through this 1.5+ states. And what we can do is we can fit the level profile to this particular state, and we see that the excitation energy we get is about 1.84 MeV with a width that's a little bit small, but is still in agreement with what we saw from those previous studies. So it was almost accidentally kind of ended up in the boron-9 game. And this is putting our results in context with the others. So as I said, as you see, they're in pretty good agreement with what we saw for these earlier studies. The width, again, it's a little bit smaller than what we expected, but still in fairly good agreements. So by this point, it was time for me to leave Texas A&M, and I was just starting a new job at Birmingham. And one of the PhD students who was in our group, Alex Brooks, had just finished his master's project, and it was all about Boron-9. So he was waiting for an experiment to take place at our MC40 cyclotron. There was a problem with the helium-3 beam line. So while we were waiting around, for a couple of weeks for the helium-3 beam to be repaired, we started discussing a little bit more deeply about what exactly is going on in this Boron-9 system and getting some practice in our matrix and some other theory type things. So one of the first things we talked about was the idea that what we need to do to actually populate this 1/2 plus state is we need to end up having our protons and neutrons actually in the right energy level. So what we can do is we can think about a very naive shell model interpretation of what's going on in the ground state. So we've got our valence proton in the 1p 3/2 orbital. This is giving us our 3/2 minus state. If we want to get to a first excited state that's a 1/2 plus, then it's going to have to come way up here to the 2s 1/2 orbital. And when we went through those previous results, what we noticed was that those experiments where you saw the 0.8 MeV instead of the 1.8 MeV answer actually use some sort of reaction mechanisms that you wouldn't really expect to actually be able to populate and put a proton into that 2s 1/2 orbital. And those where we did expect to see it was where you saw the state where I saw it before at 1.8 MeV. So okay, that's very interesting, but then that sort of leads to the question, so where is this thing at 0.8 MeV coming from? There were multiple experiments. Okay, they didn't populate the state at higher excitation, but they still saw something. So where is this signature coming from? And what we started to think about was that maybe this was arising from something known as the ghost phenomenon. So the ghost phenomenon. So what we're doing here is we're thinking about what happens to an excited state when it's undergoing particle decay. Okay. And what we know is that the ability, if we think back to when you learn in your sort of undergraduate nuclear physics courses, what we see is that the penetrability through the barrier relies exponentially on energy. So this is the example you look at in terms of alpha decay. And what we see is that the strength of this resonance can be described by this bright Wigner. And we see that this also decays very rapidly with energy. Right? So if you think about what the typical resonance shake looks like, it peaks at one energy and then it dies away with the tails as it goes away. So what we can ask ourselves is, okay, these are two slightly conflating ideas. If we go to higher energy, then actually the penetrability starts to become larger. It's almost easier for the state to decay. But then as you get to higher excitation energy, this bright Wigner is going to decay away. So we can ask ourselves, which one of these two wins? And to answer this, we can look at the width-dependent bright Wigner that takes into account these two ideas. So what we have is our Y here, which is the yield, showing us how likely is, how many times do we see a resonance decaying with a particular energy. And this depends on the width of the state, this capital gamma here. This ER is the resonance energy, so how far away we are from the energy we're looking at, and then the total width squared over 4 comes out. And what we can do is we can relate the width of this resonance to being twice the reduced width amplitude, which tells us something about the structure, the wave function of the state, times by the penetrability PL. And what we see is that actually it is possible that if this width increases faster than the bright Wigner falls off, what we get is a secondary increase in strength. So this was suggested and noted by Barker and Tricky back in 1962. And what we can do is we can look at a toy model to sort of understand this idea. So what we have on the left-hand side here is what this width-dependent bright Wigner looks like as we change our excitation energy. So around 0, where we've got this dashed dotted line, we see we've got our big resonance. As we go to higher excitation, rather than just falling away as we expect with a normal bright Wigner, we get another bump here, and then it goes down once more. And if we look at the same plot, but logarithmically, we can then see how the behavior of the width in orange is then driving this particular feature, where you see a very fast rise in its penetrability, over orders of magnitude before it sort of levels out once again. So we were kind of asking ourselves then, okay, is it possible that this is the origin of the Boron-9 system, of this 0.8 MeV peak? So what Alex went away and did then is build a R-matrix system that actually just put everything realistically for the Boron-9 system, all the widths, the penetrabilities for this particular case. And what we saw are the results shown on the screen here. So the ground state is going way up at 0 MeV excitation. And then the contribution of the ghost, we see that it's actually peaking around about 0.7, 0.8 MeV before dying away here. It's this dashed blue line as we get towards higher excitation energies. And then we also see some higher lying states. So the 5½ minus and the 5½ plus are higher energies. So this really looked like what people were seeing when they weren't populating the states was actually just the ghost of the ground states. And this was put together by Alex and published earlier this year in PhysRevC. And what we can do is we can look at an example of some of those data. So this is one of these experiments where this is what they saw. They saw this peak around about 0. MeV. And what we notice is that the line shape they have here is very asymmetric. We see that it takes longer to die away to the right-hand side, and it rises very quickly on the left-hand side. And this is also what you see from the ghost peak as well. It sort of peaks, and then it takes a long time at higher excitation energies to be able to decay away. So we thought that was kind of one mystery solved. So what we started doing is digging a little bit deeper and thinking, okay, that's one really nice piece of evidence to say that, okay, it looks like the 0.8 MeV state is from the ghost. Do we have any additional data or any models that can actually really pinpoint the fact that the right energy is this 1.8 MeV, and that is the 1½ plus state we're looking for? So what we can do is we can think about building a very simple model of Boron-9. So as I said before, what we have is we have a system where we've got our beryllium-8 nucleus. So we've just got two alpha particles touching each other. And then what we're doing is we're adding a proton into that and thinking about that proton sort of whizzing around the center. So this is very similar to an idea that takes place in chemistry, which is basically just looking at the way that different bonds are taking place as you put two different atoms together. So different types of bonds, we can have sigma bonding and pi bonding. And actually for this 1½ plus state, the expected configuration we have is the sigma bonding orbital. So analogously to what we have on the left-hand side in chemistry, the right-hand side here is showing the density of what that proton is doing as it's sort of going around the two alpha particles that are not shown apart from this white cross here, either side of the center. So we've got some sort of model for what our Boron-9 1½ plus state looks like. And what we did in the paper that is listed down below, also published earlier this year, is we started to think about what we can do in terms of showing that it has to be a 1.8 MeV. So what we can do is we can take this molecular model. We've got an idea of what it actually physically looks like. We know what the density profile looks like. And what this allows us to do is to test a very useful parameter, which is the moment of inertia. So what this means is that we're going to quantum mechanically start spinning this object around for a given spin parity, J. And what we have here in the equation, this is the quantum mechanical energy for an object that is a rigid rotor spinning around with a certain angular momentum, J. So what we have is a sort of base amount of energy. We have h bar squared over twice the moment of inertia times by the spin plus 1, because it's quantized, so you end up with this j plus 1. And then what we get is a really ugly term on the left-hand side. So this small a value is often called the Coriolis decoupling parameter. And we were kind of scratching our heads for a couple of months trying to work out how that comes from the Coriolis force, and eventually realized that it's actually nothing to do with the Coriolis effect at all. So it's just a very badly named thing indeed. And actually, there's perhaps some very interesting structural information encoded into this. So one thing we're kind of looking at is what information is kind of contained within that. So what we can do is we can think about, we've got our 1½ plus state, we start spinning it around, and we can give it different units of angular momentum. So we can do this with a few different systems. We can think about the ground state. So this is a 3½ minus state. We just keep adding units of angular momentum, and we can plot the energy versus by the spin plus 1 here. So the slope of this line is telling us what the moment of inertia is going to be. If we look at our 1/2 plus state, we see that we get this really weird zigzag pattern. So one state goes up, one goes down, one goes up, one goes down. And this is this Coriolis term that is then splitting these different states where some go higher, some go lower. So what Alex did then is said, okay, we know from the rotational bands that there are actually some states that must be the same structure as this sigma bonding that is the 1/2 plus state. We know what the energy of those states are. They've been fairly well measured. What we can do is we can use that equation we saw on the previous page, and actually we can work out if this state is here, this one is here, this one here, this one is here. Where does the 1/2 plus state have to lie? And if you put all of this information in, you fit the system, you see that the band head prediction is at 1.615 MeV energy. So again, this model is, and these higher lying states are really showing us that the energy is around 1.8 MeV. And what's also quite nice is the fact that actually the moment of inertia for this Boron-9 system is almost identical as what we see for the Beryllium-9 system as well. So at this point, after much hard work on Alex's part, I think we've got a fairly good understanding now of this 1/2 plus mystery for the Boron-9 system. There's still a few finishing touches, but we feel fairly certain that the state is at 1.8 MeV. And what we see from this is we've solved the system. We got rid of that confusing 0. MeV conundrum. That is not a real state. So the fact that it's not there in beryllium is not concerning, and that the mirror symmetry for this molecular-like system is very robust. And actually what we saw there as well was actually that whether we add a proton or a neutron to our beryllium-8 system was actually then insufficient to actually break this alpha clustering. So there are still a few things missing. We see a state at 1.8 MeV. We haven't actually done a spin parity verification. So doing something like a helium-3T measurement and measuring the differential cross-section could be one way that you could actually start to determine that. And actually, we've got a very good idea that this is the ghost, but actually it would be nicer to revisit something like a carbon-9 beta decay experiment where you're populating basically just in that excitation energy, just the ground state of boron-9. And then what we hope to see with very good statistics is that exact shape that we expected to see from the calculations we saw earlier. So A=9, beryllium, boron-9 is pretty good. So is it just lucky that in that system, the symmetry breaking was good? Are there other systems in which the symmetry breaking starts to disappear? So the next one that we started to think about was looking at the carbon-14, oxygen-14 mirror system, okay? So this originated from, there was some very high quality experimental data, really beautiful high resolution measurements, carbon-14 pp primed, and there was a result from Han et al. Where what they saw were 3 states. So they've got a slightly different plot here. Rather than plotting JJ plus 1, they've just got the angular momentum. So they saw a 0 plus state, a 2 plus state, and a 4 plus state. And what they were claiming was that this is this pi squared configuration. So here you've got 3 alpha particles all in a line, and you've got these 2 neutrons, which are having this pi bonding configuration here. And if we go from the 0 to the 2 plus to the 4 plus state, just keep spinning it, and then that's what's giving you this extra energy. So that's very cool. What we started to then look at was, okay, if you look at these calculations, so if I go back to the previous slide, so this green line here are actually the predictions, again, going back to this AMD, anti-symmetrized molecular dynamics. These were the predicted states, and they saw that they were in very close agreement. So this is what made them suggest that they saw these pi squared states. But what's really interesting is from these same calculations, for some of these states, as you go from carbon-14 to oxygen-14, they actually predicted that this one state, so for instance, this 18.4 MeV state in carbon-14, as you go to the oxygen-14 system, it actually splits into 2 states, which is really weird. I'm not sure I understand it. From the paper, it says that this is due to coupling with other configurations. Okay, and actually, this is one of the states that was seen by in that experiment that we saw before. So if we look at our oxygen-14 system, they saw that 18.4 MeV state. What we expect to see are 2 states around that particular energy in oxygen-14. And it's worth noting that their energies were about 1 MeV off. So actually, if we look at oxygen-14, we expect to see these at 16.3 and 17.0 MeV energy. So what we had was a very old data set from 2019, also run with the TechSat time projection chamber at Texas A&M. And so this is thick target inverse kinematics. We send the carbon-10 beam into a gas of helium nuclear into helium CO2. We pick up the recoil alpha particles in our silicon detectors. So what we're doing is we're sweeping through lots of different excitation energies all at once, okay? Without worrying too much about the details of that, what we're able to extract from an experiment like this is looking at what the differential cross-section is for different excitation energies in this oxygen system, okay? So for instance, if we look at this red system here, if we have a particular resonance at that right energy, what we expect to see is a large response and a large increase in the cross-section, okay? So our experimental data for 4 different angles are shown in the colors. You can see our statistics are not particularly great. We only had 5,000 particles per second. And what we've overlaid in black are the results of states that are known from the mirror system. And what we did on top of that is we added in the prediction of these 4+ states that were seen in the previous results. And if we look at these 2 central angles here at 16.3 MeV, if the same states that were seen in carbon-14 are seen in oxygen-14, we expect to see a huge increase at this particular angle in the cross-section, and obviously there's no such corresponding increase in our data here. And actually, there was a very nice result as well that came out last year from Martel, and they did basically the same experiment, carbon-10, alpha-alpha, and they also didn't see these states. So it wasn't just something that we were unable to see in our results. So then this is a really interesting case. So they say that they see these pi-squared configurations in carbon-14, but we don't see these in oxygen-14. So we started to think, okay, there's a few different scenarios of what exactly is going on. And actually, perhaps one of the most likely one is actually the state that was seen in that previous experiment. Maybe it wasn't actually a 4+ state at all. So the way that they were able to actually determine what the spin was of that state, they were maybe pushing the boundaries of where that particular model could be used. So that means that perhaps what they saw isn't really a linear chain, a pi-squared, a linear chain configuration at all. That's one possibility. The other possibility is that actually in these calculations, this mirror symmetry breaking was actually not quite being correctly dealt with and being replicated. So maybe somehow the splitting means that rather than going to slightly different energies, maybe they both jump up way in excitation energy and we're looking far too low in our energy system. Maybe somehow turning your 2 neutrons into 2 protons is somehow killing the state, and it's not possible for that state. It's no longer a resonance in the mirror system. Maybe that's one option, or some other sort of model limitation. And of course, you always have to make sure that you go through and ensure that the problem isn't with the experiment and that you've sort of covered all possibilities for stupid things that you've kind of not thought about. So all conceivable issues, actually, we went through some of those and actually showed that we've kind of accounted for all conceivable issues. So that it doesn't seem like the problem is actually with the experimental data. And very well timed for this talk. These results were actually published in PRC on Wednesday. So that was good timing. So where does that leave us in terms of future prospects, in terms of mirror systems? So what we saw was that this mirror symmetry, where we're changing our protons and neutrons, we see the same state, but just with very small shifts in what the energy is going to be. It seems now, after some hard work, that actually this Boron-9 1.5+ state seems to be fairly well understood. And we know that the mirror symmetry then is robust between beryllium and Boron-9. But what we see is that there are some cases where where theoretical calculations do predict the breakdown of this mirror symmetry, and you see this different behavior for these 2 systems. But we've yet to actually be able to see that actually play out experimentally. And as I said at the start, actually testing the limits of this mirror symmetry can be very useful. So in many cases, when you do nuclear astrophysics cross-section predictions, what you often use is the mirror system. You know where the states are, you know what the rough widths are, and then you can use that as a first-order approximation. So if we find out that actually in certain scenarios, this mirror symmetry is not very useful, we can avoid making scurrilous predictions for very sensitive measurements. And then more broadly, we can start to think, do we actually understand why these certain states occur near thresholds? And over the years, there are lots of very complicated theoretical explanations that, again, I must confess, I don't really understand in particular detail. So there's a very nice one here about the idea of treating the nucleus as an open quantum system that seems to in some way sort of force the concentration of these states to be closer towards the threshold. This was even something that Wigner discussed way back in the past with this idea of this Wigner cusp. And then you see fancy ideas such as superradiance, where you have overlapping states, and one state sort of saps all the strength from one. So one becomes a very, very strong state, one becomes a very weak state. And again, that's a really interesting idea when thinking about clustering. So with that, I would like to thank all the various people who've helped with the data for this presentation. In particular, thanks to a student, Alex Brooks, from whom did the majority of the work on the Boron-9 1.5+ state. And I'd like to thank all of you for listening. Thank you.